Okay, so now that we've done that quiz, for those of you who came in late, make sure you see me at the end of class because I want to make sure you're on this roster because it's changed since the last time. So other than that, let's move on. We are going to continue with 10.2.
We start with scalar multiplication.
So for the time being, up to like 10.4, most of what we're going to be doing is definitions. Is just par for the course. We need to actually understand the things we're going to be talking about. In 10.5, we'll actually get down to doing some legitimate problems. But for now, I'm just going to sort of tell you these are what things are, and it's still important stuff though. We're going to be using all this information in the background, so still pay attention, but don't expect to be too excited by this. You'll have more excitement than you can manage pretty soon, I promise. But for now, let's just get through some definitions. We spoke about what vectors are, things that have magnitude and direction. We spoke about how we represent them geometrically, how we can write them down in notation. We spoke about adding two vectors, what that means geometrically. We're actually going to do that algebraically today. And what it means to be a scalar multiple. And now we are going to move on to talk about parallel. How do we know two vectors are parallel? Yeah. They don't have to have the same magnitude. Same direction. How do we know if two vectors have the same direction?
They could be on factors of each other, right?
Scalar multiple is the word we want to use. It's not good enough to just say factor, right? When in the previous classes when we said factor, it's just you have one number times another number. A scalar multiple means you have a scalar times a vector. It's a very different kind of quantity. So the answer is if they are, or you can say if one is a scalar multiple of the other. Alright, so i.e. A and B are parallel if and only if A is a constant times B, or C is a scalar. Very important thing to know when you have the same direction. Magnitude usually won't matter, but it matters if we're doing physical applications, like the magnitude usually will translate to the amount of force something is having. But in general, we don't care about magnitude too much. Parallel just means they have the same direction. It means one is a scalar multiple of the other. Usually we say a non-zero scalar multiple. Zero can work. The zero vector is actually parallel and perpendicular to everything. It's sort of a weird vector.
C is meant to represent a constant right there.
Yeah, so C is a constant. Remember the notation. If I write an arrow over it, it is a vector. If I write no arrow over it, it is a constant. It's a very, very important distinction. Okay. All right, let's move on. What do we talk about? The negative. Right. So here they don't have to be, as I said, the same magnitude. You can have someone like that and then someone slightly longer. It's also possible to go in the opposite direction, but they will never touch. That's also fine because your C could be negative and it reverses the direction. But as long as they will never meet, you say they're parallel. We also want to talk about the negative. Let V be a vector. The negative of V is denoted minus B. It is the vector having the same magnitude but opposite direction. B is the guy like this, or minus B would be the guy like this. Same length here. I have to introduce that notation. You just write absolute values over the B. So they'll have the same length, but they go in exact opposite directions. That's called the negative vector. Right? So pretty much when the scalar multiple is -1, you get that guy. Okay, now let's talk about vector subtraction. When I write the notation a minus b, what does that mean? This means a plus the negative of b, right? Where the negative of b is defined this way. You just take b and flip it around, but then you do the same sort of process as adding, right? So if we have a here, and we have let's do b here, what will a minus b look like? Well, so first realize that minus b, what would that look like? It will point actually up, right? So this means that if I look at something like a minus b, what's going to happen is I'm going to have a, and then I'm going to add that to minus b. Remember how we added vectors? I put the initial point at the head of the first one, and then I continue here. This guy is minus b. And so with this new vector here, which I don't have a different colored chalk to represent, is the vector a minus b. As opposed to the vector a plus b, in which case I would do a like this, and then I would just add b to the end of it, so it will actually go down like this, and this would be the vector a plus b. So the vector a plus b will point down in that direction, down and to the right, while the vector a minus b will point up and slightly to the left, right? You think of a minus b as a plus the negative of b. The negative of b is simply taking b and flipping it in the opposite direction. So that's what it means to subtract two vectors. I thought I saw a hand go up. Did someone have a question?
I'm personally, I'm still lost. Like, just from, I got a little confused from the second drawing right there.
So this is the picture for A, that's the picture for B.
I know.
It's okay?
No, that one.
Yeah. So first you have to figure out what minus B is.
Okay.
Right? So A minus B, I think of it as A plus the negative of B.
Right.
So I'm going to just take A and add it to that guy.
Okay.
So what we do is, you start at the initial point of A, you follow it to the terminal point, and then from there you start the initial point of minus B and follow it to its terminal point.
And that terminal, the
And
final
then-
terminal point would
Right.
be
And then the initial point of the very first step to the final point of the very last step, the vector that does that is the negative.
I see.
Right? Similar for adding, A, you move from the initial point of A to here, you start from there and you attach B. The vector that goes from the first step here to the last step here is the sum.
Okay.
of the two.
I get it.
So you're just like attaching things head to head.
All right.
Right? And it just so happens, subtraction just means you're attaching the negative instead of the positive.
Right.
So you're sort of flipping things.
I see.
This concept has a lot of applications to physics for it, and I'll do an example of that. We'll do a couple examples of that so you can see. What else do I need to tell you about? So this subtraction. Let's talk about components of vectors. So we're going to talk more now about less the geometric side of things and more the algebraic side of things. We need to write down formulas and stuff. Let's jump into that. Talk about the components of vectors. We'll usually use the rectangular Cartesian coordinate system to represent vectors, but in higher level mathematics that's not necessarily true, but we're going to always be doing this. So represent it using coordinate systems. Example, it looks sort of like a point, like you'd write down a coordinate, but you can distinguish it as a vector by a certain notation. So for example, I can write A equals, I write those sharp-edged parentheses, A1 comma A2. So this is a 2D vector. So the difference is, if I write down A1 comma A2, and I write regular parentheses, what am I actually saying? Well, it's the point, this is A1, that's A2. I'm plotting that point, and that's it. If I write this down, what am I saying? Well, similarly, I go by the coordinate system, but now I start at the origin, and I hit that point. And I'm talking about that vector, right? So again, pay attention to detail here, very subtle, right? If I write this, I mean a point. If I write this, I mean a vector. Two different things. This is just a location. This is telling me magnitude and direction, right? That being said, I always sort of do this, and students, they don't realize why I'm so pedantic with certain definitions. Like for example, if I say, I want your homework like this is how you should put the title, give me the topic number, give me the homework number, right? Some students might, they write their name, but they don't write the homework number, they put the topic number. And I'll take off points for that. Or, if they write a notation like they write this when they mean this, I'll take off points for that. They're like, you know what I mean, why are you being so mean, you complain, oh, you know what's going on, yeah, I understand the problem. So the thing is, the higher up you go, the notations get there are little subtle changes that can make a world of difference. Like paying attention to detail and knowing that this is the instruction, this is how it has to go, saves you a lot of headache, right? Trust me, I've been in classes where I've misunderstood notation, I literally got nothing, and at some point where the notation cleared up, I'm like, oh, everything fell into place, right? So be careful, these subtle things matter. Notice also that I didn't write an arrow over the components, right? They're not supposed to be arrows over the components, right? These are just scalars inside here, right? But you're just sort of using the coordinate system to represent the vector. So pay attention to the notation, pay attention to the subtleties, because they can come back to bite you if you don't, right? So, or I can do something like A is equal to component A1, A2, A3, and this is a 3D vector, in which case if I'm graphing something like that, find A1 on the x-axis, find A2 on the y-axis, so I know those guys will meet somewhere in the xy plane. Then I go and I find A3 on the z-axis, and what happens is this sort of creates a rectangular box, right, where the edge of that box connected to the origin. Well, it's sort of point. Let me draw something that looks nicer. Let's say A1 is over here, A2 is over here, A3 is over here. So you connect those in the XY plane, but what happens is when you add the Z coordinate, you end up with this rectangular box, and it goes from the origin to that corner over here. So that would look like the vector A. Just follow the 3D coordinate system, and that can also work. Here, A1, A2, A3 are called the components of the vector A. So A1 is equal to, you can call it the X component, Y component, and J component. Z component. So you go by the XYZ coordinate system. Another definition. A position vector is a vector whose initial point is the origin. So far, I've only been drawing position vectors. You see, like this vector here, I didn't have to draw it in that position. I could have drawn it over here. Just make sure I moved over by a distance A1 and up by a distance A2. I can draw it in any location I prefer. When I choose the location to be the origin, it's called a position vector, because it will give me, for example, the position on a curve, right, which we're going to talk about. Right? One of the reasons why we need vectors is it's how we locate things in 3 space. It's one of the most efficient ways to locate things in higher dimensions. You don't really need it in 2D, but in 3D and above, vectors help us locate things. Figure out a lot of formulas and stuff like that. Okay.
Is there a way to like denote that it's a position vector in the writing? No?
No. It's just something you know to use. Well, like we'll see some context where I specifically use position vectors to figure certain things out. Like when we want to figure out the equation of lines and planes, we're going to be using position vectors to figure that out. So, if, for example, A equals A1, A2 is a position vector. Then its initial point is 0, 0, and its terminal point is A1, A2. Notice I use parentheses and not the sharp edge brackets. Several times position vectors are used in the same way we use points, but we'll get to those subtleties later on. What else do I want to tell you about? That's how to figure out how to make our own vectors, which is going to be super important pretty soon. Creating a vector given its initial and final point. suppose A is a vector the initial point is A1, A2, A3, and final point is B1, B2, B3. If I want to algebraically write down a vector that goes from that point to that point, or maybe let's start with 2D first so I can draw a nicer picture. It'll be a common theme. Usually what I say works for 2D will work for 3D, so you can even imagine with 3 components if you'd like. So let's say in 2 dimensions, I have something here at the point A1, comma A2, and I know a point is over here at B1, comma B2, and I'm saying, here's a vector that goes from this point to that point. How do I actually write it down? Right, so I'm calling this a vector A. So the thing is, what we do is we want to write it down using components. These components actually tell you the distance that you move in each of these directions, right? So the x component tells you how far you move in the x direction, right? If the x component is positive, you move to the right. If it's negative, you move to the left. Similarly, this tells you how you move in the y direction. If it's positive, you move in the positive y direction. If it's negative, you move in the negative y direction, and so on and so forth. So what I want to do is figure out how far do I have to move over to the right, and then how far up, right? That's the question. What is this distance? What is that distance? How do you think I figure out those?
The x component is b1 minus a1.
Right, you subtract the x coordinates, right? So here, this would be an a1 here, this would be a b1 here. What I'm actually doing is asking, what is this distance, right? So the x component is just going to be b1 minus a1. Similarly, over here, this hits at a2. Over here, this hits at b2. If I want to know what is the vertical component, I just subtract those two. So in other words, A would be the vector B1 minus A1, comma B2 minus A2. Did I have an example for that? I did have one for that example. This might be familiar to a lot of you. I know you might be bored, especially if you've done physics before, you'd have seen all this, but I need to make sure that everyone is on the same page. So that when I start killing you guys later, you can't complain. So example. Find the vector with initial point. Make up any random numbers here, but I already wrote something down. So 4 minus 2, comma 0, and final point 1, 3, 5. Time. So, if I call the vector A, I can say A would be equal to, I open those sharp edged brackets because I'm going to write down a vector. So this is the initial, this is the final. Basically, you're going to take the final point minus the initial point. That's how it's going to work. Right? So you're going to say, if the initial point is this, the final point is that. For each component, I'm going to take final minus initial. So 1 minus 4, comma 3 minus a minus 2, comma 5 minus 0. So it's final minus initial, always. Right? That's to ensure that you go in the right direction. It's always final minus initial. So this means your vector A is simply, you can write that vector down as minus 3 5, 5. That is the vector that starts at this point and moves to that point. Or this is just a vector in general, it can be anywhere. But I know that if I put it so its initial point sits here, the final point will end up here. Because all I'm doing is figuring out the components, just figuring out the length of these guys. What else do I have to tell you? Let's talk about length. Length, another word for it is magnitude. So, so let's say I had a vector here, starts at A1, A2, goes up to B1, B2. How do I figure out the size of this, the length?
The distance formula.
Distance formula. Exactly, which is derived by Pythagoras' theorem. So you can think of it as using Pythagoras' theorem. So this is so by distance formula, which happens by way of Pythagoras' theorem, the length of A is, just take the square root of this minus that, B1 minus A1 squared plus B2 minus A2 squared. So you just use the distance formula. Notation. The length of a vector A is, you write this, or in some textbooks you might write that. They write a double absolute values. Either one is fine for us because, as you can see here, with that arrow in there, I know when you put absolute values, what you need is the length. But there are contexts where you might need an extra notation. So if you see either of these, it's the same thing. For now, just think of it as just the length of the vector. And it will go by these components. So in other words, if A is equal to this A1, A2, A3, what you can do is you can think of it as a position vector where the initial is 0 and find the length that way. The magnitude of A is just going to be the square root of A1 squared plus A2 squared plus A3 squared. Formula. So if you just take the radical of the sum of the square of the components, it actually gives you the magnitude of the vector. A1, A2, then magnitude of A. You just adjust the formula for how many dimensions you're working with. Usually we'll be in 2 or 3 dimensions. But you could extend this formula to 4 dimensions and further. Any questions so far? It's just a bunch of definitions really, but if you have any questions you can stop me. We can add, subtract vectors by adding, subtracting their components. What does that mean? If I know that A is equal to A1, A2, A3, B is equal to B1, B2, B3, then thankfully, this is still consistent with the geometric interpretation that we had before. If I say A plus B, I can literally write down those components as A1 plus B1, comma, A2 plus B2, comma, A3 plus B3. And this will be the vector that if you attach this guy to that guy and draw that, it will actually be that guy. Or A minus B, A1 minus B1, comma, A2 minus B2, comma, A3 minus B3. Right? So if you know your vectors as components, you can add or subtract the components to add or subtract your vectors. Right? You don't need to like draw a picture and then figure out, put it on a grid or something like that. You can literally just do the components and they will actually work out. Because again, it comes down to distances. You're measuring distances and you can subtract one from the other. You need to do it now. You don't have to write things like this. I'm just doing it. You can skip this and just write that. So if I actually wrote these as position vectors, right, let's say I made that A, where this guy here was 1, that guy here was 2, and I wrote B, which goes minus 2, and positive 1. That's B. You can sort of use the parallelogram wall. Your A plus B would be something like this. A plus B. And what you'll do is you'll notice that he goes a little bit to the left and then up really fast, right? He moves 1 unit over. So technically this should be like, right? He will actually move 1 unit over here and then 3 units up here. So this will be at 3 now. Any questions on that? So algebraically, this is what happens. Geometrically, this is actually what's happening. The picture will match what's going on algebraically. Yes.
Can you explain the last average?
The what?
Can you explain the
Okay, so this is just a geometric thing that helps you out. Let's say you have a vector here, A, and you're connected to a vector B. And you want to figure out the sum. A quick way to do it is to make a parallelogram. Right? So draw another side here that's parallel to B. Right? Draw another side here that's parallel to A. Right? And the vector that goes from this corner to that corner is going to be the sum. Right? It's just the diagonal of the parallelogram. So that's sort of what I did here. To figure out what the sum was, because I didn't have this attached to that, what I did was I just make a line parallel to this, a line parallel to that, and then I connected the initial point to the opposite point. It's the same thing. So it's like, even if my B was over here, I could have just taken them, picked them up, put them here, and just connect the ends, as I was doing before. So you can do that with the parallelogram. How about scalar multiples again? You can algebraically find scalar multiples by simply multiplying each component. So if A is this, then if I take C times A, where C is a scalar, it would just be C times A1, C times A2, C times A3. Things like that. You should know how to algebraically find the scalar multiple. You just multiply the components. These are then the vector 1 and 2. Find 3A. Here, 3A will simply be 3 times 1 and 3 times 2 equals 3.6. So this guy's 1, 2. That's my A. Then the guy that goes 3, 6 should fall right in line. That's a 6. So this guy here is A. Well, this huge guy here is 3A. It will have the same direction, but it will be 3 times the magnitude. Algebraically, if you don't care about the picture, you simply multiply the components here by the scalar. What else do we have here? Okay, try these. Find the magnitude of A, find a plus b, find a minus b, find 2a, find 3b, find 2a minus 3b. Okay, what's the magnitude of A?
Radical 14.
So take the radical of the sum of each component squared. So it's going to be 1 squared plus 2 squared plus 3 squared. So it's 1 plus 4, which is 5, plus 9, which is radical 14. What's the vector A plus B? Notice, by the way, this is a scalar. Anyway, A plus B.
3 to
Okay.
8. -3
Okay.
to 8. Yeah.
Alright, so you just add them. 1 plus or minus 4, comma, 2 plus 0, comma, 3 plus 5, plus minus 3, 2, 8. The subtraction would be 1 minus 4, comma, 2 minus 0, comma, 3 minus 5, which would be 5, 2, minus 2. Two A would be what?
So that would be
Yeah, so there's 2 times 1, 2 times 2, 2 times 3, which is just 2, 4, 6, 3B, 2, 3. A minus 3B would be what? 14, 4. Do I need to explain where that came from? Some of you are going right. Calculation.
Oh,
Okay.
Oh,
Do I have anyone who wants to shout that aloud? Declare that to the class. And then we check back with you in a couple weeks. Properties. You can see our vectors. C and D are scalars. Now I'm going to write down a bunch of stuff. It's going to seem obvious because in vectors, that's just how they work. But there are contexts in mathematics where things like this are not obvious. So just bear with me. It turns out that A plus B is the same as B plus A. We have commutative addition. It also turns out that we have associativity of addition. So A plus B plus C. If I'm adding three things, it actually does not matter which two I add first. So if I have several things, I just add them two at a time, and it doesn't matter what order I add them in. Because we have associativity. Turns out that A plus the 0 vector is just the vector A, where of course the 0 vector in our context happens to be the vector with all components 0. There are contexts in which that's not the case, although if you're not a math major, you probably won't study things like that anyway, but just want to point that out. Or, if you take A plus the negative of A, the result is the 0 vector. 5. If I take a scalar times a sum of vectors, it's the same. I can apply the distributive law with scalars. It's the same as taking the scalar of A and adding it to the scalar of B. It works when I have two scalars as well. This guy's going to be C times A plus D times A. CD times A is equal to C times DA. And yes, 1 times A is actually A. Don't be fooled. Okay, let's see. Let's talk about the standard basis vectors. In 2D, we call these guys I and J. This is the vector 1, 0. This is the vector 0, 1. So I is the vector that runs along the x-axis and it has length 1. This is the vector we call I. The guy that runs along the y-axis having length 1, we call that guy J. Right? So if I say I and J, this is what I mean, and I will put an arrow over it. Because they are actually vectors. In 3D, it's sort of what you would expect as well. I would be the 3 component vector with 1 in the x-coordinate, J has 1 in the second coordinate, and the third one is called K. This is 1 in the z component. These are called the standard basis vectors. You don't need to know what a basis is, but basically what you have to know at this point is that these guys are non-parallel vectors that we can easily express any other vectors in terms of them. So for example, we can write any vector in terms of these basis vectors. So, for example, if I have the vector A is A1, comma A2, comma A3, the idea is knowing what I know about addition, I can write this as that. Plus 0, 0, A3. I know how to add these guys so I can understand. If I add these three, I'll get those three. And because A1, the components are scalars, and I know the distributive law, I can actually factor an A1 out. And it turns out that these guys are my standard basis vectors. So I can rewrite this as A1I plus A2J plus A3K. What this does, it gives me an alternative notation for my vectors. And pretty much any textbook will use both of these notations, so you just have to recognize when something is being used. So for example, if I write the vector 1, 2, 3, it's the same as saying 1i plus 2j plus 3k. It's the same thing, right? Just a different notation. Do not mix up the notations, meaning if you're going to write brackets, you can't write the I, J, and K here. Right? So something like that is wrong. Right? You have to choose if you're going to do the I, J, or K, or choose that you're going to do the brackets. Right? Or you can't do like, 1i plus 2j plus 3k, and then put brackets on that. That's also wrong. It's one or the other. Either you're doing the brackets and the commas, or you're doing the ijks and the sums. Right? Choose. Personally, I like this way because it's less writing for me. So even if I see a problem in this way, I'd rewrite it in that way and use that. But you don't have to. We want to talk about unit vectors. These are just vectors with magnitude 1. They help us with direction, as well as they help us to scale things to any desired scale we like. Definition. So if A is not the zero vector, then a unit vector, which they often denote it U, is the vector the same or opposite direction of A given by, so that continues over here. Anyone know the formula for U? It's A over the magnitude of it.
Oh, yeah.
So A is some random vector of some random length that's not the zero vector. If I want to get a vector U that has length 1, then U is just going to be take A divided by its magnitude. parallel to the vector A equals 2, minus 1, 3. Call the first unit vector u1. What's u1? Yep.
2 over radical 14.
Right. So you do this, and you divide by the magnitude, which is just going to be radical 2 squared plus 1 squared plus 3 squared, which we saw earlier, that was radical 14. So this I can think of 2, blah, 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 all over radical 14, which is the same as taking the scalar 1 over radical 14 times this vector. So I can actually bring it in 2 over radical 14, comma, minus 1 over radical 14, comma, 3 over radical 14. So this will have the same direction as that, except it will have length 1, where this guy has length radical 14. Tell me about another unit vector. Right, just the negative of this guy. Right, so it'll just be minus 2 over radical 14, 1 over radical 14, 3 over radical 14. That's that. So if u1 does that, then u2 does that. They're still unit vectors. Yeah.
What did they 3 there?
This would be negative.
Those are the only 2 possible.
Yes. There are no other unit vectors. You can only have 2 here.
I'm just a little confused. Why do they have to be negative, like opposite signs for the second vector? You made the negative 2 over radical 14 and 1 over that. Like why? Exactly.
It's the only way to maintain the same, it's the only way to keep them parallel.
Oh, okay.
If I multiply by any other number,
It won't be parallel. Okay.
it would change the length. If I multiply by a scalar, it will stay parallel. The length wouldn't be 1 anymore. So I have to multiply by minus 1 to keep the length at 1. Just going to do one application. I'd like to do an application where the length actually does matter. Of course, one of the simplest ones is mechanics. So I have, did I say 50 pound? 50. I don't know why you'll hang a 50-pound weight from this, but okay. There's a 50-pound weight being attached by strings, and basically there are tension forces holding this thing together, T1 and T2. You can put T1 over here, T2 over there, but it doesn't really matter. And what I do know is this angle here is pi over 4, while this angle here is pi over 3. And the question is, what are the tension forces? So this thing is in what we call equilibrium. Obviously, if this thing was too heavy, the string's going to manage it, it will just pop, right? And they'll fall off. But the fact that it's holding them stable, what does that mean? Has anyone done physics? Sorry, no. What's equal to the tension? So it must mean, well, in the two-dimensional thing, you can only think of really just two sort of directions. You can either move up or down, right? So you're thinking, the things that are pulling me up must be equal to the thing that's pulling me down. That's why we're not moving, right?
Right.
So we know that, for example, that T1 plus T2, if I think of these guys as vectors, which is what one of the easiest ways to conceptualize this, it must equal to what vector?
The opposite of the opposite of like the downward weight.
Okay, so if I think of this as a vector, this 50-pound weight, how would I write that as a vector?
It's to negative W, right? For negative weight.
Negative W is a scalar. We actually know what the magnitude of this force is.
0, 50.
0, 50 is not correct. But yes, the first one is 0.
0, negative
0, negative 50. Right? Remember, positive means we're going up. This thing, the weight is actually pulling things down. So all I need to do is make sure that the sum of these vectors equal that vector. Right? Because the system is stable now, it's not moving.
Yeah.
So now, how do I actually figure out what these guys are?
There's a formula. There's like a way to set it up.
Sure, if we could find the form for T1 and T2, that will help a lot, because we know that the force is just the magnitude of the vector. That's sort of the concept, right?
Isn't it T1 like cosine, for example, T1 cosine pi over 4 plus T1 sine pi over 4?
So here's that diagram again. Sure, we know that this here is pi over 4. Yeah, we can sort of break this in half and think of these as two right triangles. This would be okay. So what were you saying now? So this is T1.
Yeah, so T1 is equal to T1 is equal to T1 times cosine pi over 4 plus T1 sine pi over 4 for the x component and the y component.
Right, so you want to figure out the components of the vector, which is what we want to do. Right, so this will be the length here, you said as well?
That would be that's the sine one, so that's T1 sine pi over 4.
This is the magnitude of T1 times sine pi over 4. This guy here will be the magnitude of T1 cosine pi over 4. Right? Because there's that rule that says this angle would be equal to this angle. And then SOHCAHTOA helps you figure this out. So I know that's what T1 looks like. Similarly, I can do the components of this guy. Right? I know the opposite has to be the sine, so this is going to be T2 sine pi over 3. The adjacent is the cosine, T2 cosine pi over 3. So this gives us the following equation. The T1 vector is, how do I write the components of the T1 vector? Now that we have that, how do I write down the components?
T1 cosine pi over 4 sine pi over 4.
No? We're thinking of them as vectors. Directions matter.
Oh, that's a negative.
Negative,
Cosine.
because T1 moves to the left and up. So the x component must be negative, right? So this would be T1. What's cosine of pi over 4? You're taking too long. Took too long. Okay, plus, comma, what's the other one? What's the sine of pi over 4? It's the same thing. All right, so if I do that plus,
It's actually sine pi over 3.
where,
Are the angles different?
I'm only looking at T1.
Oh, okay, I'm sorry.
I'm just writing this vector, I'm just thinking of this vector, and then I'm going to do that vector.
Sorry, I thought you were adding them.
I'm not adding them yet, I'm going to.
Okay.
I just want to figure out the components for them. So T2 is going to be T2. I want the x component, which is moving to the right, so it's going to be positive. What's cosine pi over 3? It's a half. Comma T2. Sine pi over 3 going up. What's sine pi over 3?
Negative.
Pi over 3 over 2. Now if I do all that, I get 0 comma minus 50. So in other words, if I take minus T1 over radical 2 plus T2 over 2, that will give me 0. And if I get T2 over 2, and if I take T1 over radical 2 plus T2 times radical 3 over 2, that should give me minus 50. So now I have a system of equations, 2 equations, 2 unknowns. We solve simultaneously. Time's pretty much up. Because I want to leave you with a problem, so I don't want to spend time solving this. Solve simultaneously, which is college algebra, so I probably don't even have to do it for you. Find T1 and T2. Here's a problem I want you guys to think about for the next time. A large boat is being pulled by 2 smaller tugboats. So the big boat here, and there are 2 little tugboats. So, if I look at the axis of the ship here, this tugboat is pulling at an angle of pi over 6, and this guy has angle minus pi over 4. And I actually know what speeds they're moving at. This guy is moving at 5 meters per second. This guy is moving at 2 meters per second. And here's the question. That you can answer by thinking of this in terms of vectors. In what direction will the boat move? And with what speed? So think about that for next time and actually find the answers to this. And we'll pick up there. We actually did complete 10.2, by the way. So in addition to doing this, do the homework for 10.2. So that's it. See you guys next week. Well, see you guys Thursday.